For a long time, humanity believed that the universe followed a certain order. Stars were born, planets formed, galaxies evolved, and everything happened according to rules we thought we understood. But every once in a while, an observation arrives that forces the entire scientific community to stop, look again, and admit something uncomfortable. We were wrong. The James Webb Space Telescope has just delivered one of those moments. Across multiple corners of the cosmos, Webb has revealed events and structures that should not exist the way they do. Young stars forging crystals that somehow end up frozen inside comets. Dying stars exhaling their final breath and turning destruction into the raw ingredients for future planets. Supermassive black holes that were thought to be ejecting matter, now revealed to be quietly feeding instead. Entire populations of galaxies that defy every category astronomers have ever created, sitting at the edge of cosmic time like unanswered questions. And massive stars locked in a slow, violent dance, carving perfect spirals of dust through space for centuries, exposing patterns no telescope had ever seen before. These discoveries are not isolated. Together, they tell a single story. The universe is far more interconnected, more precise and more surprising than our models ever allowed. James Webb didn't just capture beautiful images. It exposed hidden mechanisms, corrected decades of assumptions, and forced scientists to rewrite explanations they thought were already settled. This is not about one star, one galaxy, or one strange system. This is about a telescope that just stopped the world, because what it revealed can no longer be ignored. For decades, astronomers were confronted with a contradiction that never quite made sense. Comets located at the frozen outskirts of planetary systems, including our own Kuiper Belt and Oort cloud, were found to contain crystalline silicates, minerals that can only form under extreme heat. These icy bodies spend most of their existence in regions so cold that such crystals should be impossible to create there. Scientists could identify the crystals, but they could not explain how they formed or how they traveled from hot environments to the coldest edges of a system. By looking beyond our solar system, the James Webb Space Telescope finally delivered the missing link, showing for the first time that crystalline silicates are forged in the hot inner regions of a disk of gas and dust surrounding a very young, actively forming sun-like star, directly connecting intense heat with distant frozen material. The star at the center of this discovery is a protostar known as EC53, located about 1,300 light-years away in the Serpens Nebula. Unlike many young stars that behave erratically, EC53 follows a remarkably predictable cycle. Approximately every 18 months, the star enters a powerful outburst phase lasting about 100 days. During these periods, it dramatically increases its consumption of nearby gas and dust from the surrounding disk, while simultaneously ejecting part of that material in the form of strong jets and winds. Webb's observations revealed that these layered outflows are not gentle breezes, but energetic streams capable of lifting newly formed crystalline silicates from the inner disk. These expulsions appear strong enough to fling the crystals outward, potentially delivering them to the cold, distant regions of the disk where comets may one day form. Using Webb's mid-infrared instrument, researchers collected 2 sets of highly detailed spectra that allowed them to identify specific silicates in the dust near EC53, including forsterite and enstatite, minerals that are also common on Earth. But Webb did more than identify their composition. It precisely mapped where these crystals are located before, during, and after the star's outburst phases. By observing EC53 when it was relatively quiet and when it was actively devouring material, scientists could track how the crystals migrate through the system. The data revealed that the star's layered outflows act like a transport network, carrying these superfine particles outward along the disk. For the first time, astronomers could directly observe not just the presence of crystals, but the mechanism that redistributes them across a forming planetary system. Webb's data also showed narrow, high-velocity jets of hot gas near the star's poles, along with slightly cooler and slower outflows originating from the innermost and hottest parts of the disk. Together, these flows form a dynamic system that spreads crystalline material throughout the disk over time. EC53 is still wrapped in dust and may remain so for another 100,000 years, but over millions of years, countless collisions between tiny dust grains and pebbles will gradually build larger rocks, eventually leading to the formation of planets. As the disk settles and clears, a sun-like star will remain at the center of a planetary system seeded with crystalline silicates. Webb has shown that these crystals are not anomalies or accidents, but a natural consequence of early stellar evolution, forged close to young stars and deliberately transported outward to become part of future worlds. When the James Webb Space Telescope turned its gaze toward the Helix Nebula, it was not simply capturing a beautiful cosmic structure, it was offering humanity a preview of a fate that may one day await our own sun and planetary system. The Helix Nebula represents a late stage in stellar evolution, where a dying star sheds its outer layers and releases vast amounts of gas and dust back into space. Webb's high-resolution near-infrared vision zoomed deep into this process, revealing the intricate structure of the material being expelled. What once appeared as a soft, glowing ring now resolves into a complex system of sculpted gas, shaped by interactions between fast, blistering stellar winds and slower shells of material ejected earlier in the star's life. In this single image, Webb shows stellar death not as an end, but as an active, dynamic transformation that feeds the next generation of cosmic structures. One of the most striking features revealed by Webb is the presence of countless pillars that resemble comets, each with an extended tail pointing away from the nebula's center. These structures trace the inner edge of an expanding shell of gas and dust, and they exist because of a violent interaction. Fast-moving, extremely hot winds from the dying star slam into older, slower, and cooler material that was released earlier, carving and sculpting the nebula into its iconic shape. Webb's near-infrared resolution brings these knots into sharp focus, revealing details that were only hinted at by previous telescopes. Compared to earlier images from Hubble and Spitzer, Webb exposes a far clearer transition between different layers of gas, allowing astronomers to see how energy, motion, and time combine to shape the final architecture of a dying star's surroundings. At the heart of the Helix Nebula lies a blazing white dwarf, the exposed core of the dying star, whose intense radiation energizes everything around it. Although the white dwarf itself lies just outside the frame of Webb's image, its influence dominates the scene. Webb's color mapping reveals a clear stratification of temperature and chemistry across the nebula. Closest to the white dwarf, gas is heated to extreme temperatures and glows in hues associated with ionized material. Farther out, the gas cools, allowing hydrogen atoms to pair up into molecular hydrogen, while even farther from the center, the coldest regions emerge, where gas thins and dust can begin to form. Within these cooler, shielded pockets, more complex molecules can survive and grow. This layered structure shows how stellar material transitions from extreme radiation to protected environments capable of seeding future planetary systems. What makes the Helix Nebula so profound is not just its beauty, but its role in the cosmic cycle of creation. Webb's observations show that the gas and dust expelled by the dying star do not simply disperse randomly into space. Instead, they are recycled, becoming raw material for future generations of stars and planets. Earlier studies suggested that complex molecules could form in these environments, but Webb's resolution reveals exactly where this chemistry happens, inside dark, shielded pockets embedded within the nebula. Located about 650 light-years away in the constellation Aquarius, the Helix Nebula now stands as one of the clearest demonstrations of how stellar death fuels cosmic rebirth. Through Webb's eyes, the nebula transforms from a static object into a living process, where a star's final breath becomes the foundation for worlds yet to exist. At the center of the Circinus galaxy, located about 13 million light-years away, lies a supermassive black hole that has shaped the evolution of its entire host galaxy. For decades, astronomers knew this black hole was active, but they could not directly see what was happening in its immediate surroundings. The region is flooded with intense starlight and wrapped in thick clouds of gas and dust, making it almost impossible to separate one structure from another. What scientists could detect was a powerful excess of infrared light coming from the galaxy's core, but the true source of that emission remained unresolved. Was it matter being violently ejected outward in massive outflows, or was something else happening closer to the black hole itself? With the James Webb Space Telescope, astronomers finally gained the clarity needed to challenge long-standing assumptions. Webb delivered the sharpest infrared view ever obtained of a black hole's surroundings, allowing scientists to investigate the heart of Circinus in unprecedented detail and forcing them to confront the possibility that decades of modeling may have been built on incomplete information. Before Webb, astronomers had to rely on indirect methods to study Circinus. Because the central region could not be resolved, researchers measured the total light coming from the galaxy's core across a wide range of wavelengths and fed that data into theoretical models. These models attempted to separate the contributions from different structures, such as the torus of gas and dust surrounding the black hole, the accretion disk spiraling inward, and the hot outflows streaming away from the center. However, these approaches consistently ran into the same problem. Telescopes detected excess infrared emission from hot dust that could not be confidently attributed to any single component. Since the 1990s, scientists debated whether this excess came primarily from outflows or from material falling inward. Most models favored outflows as the dominant source, largely because there was no way to filter out the surrounding starlight or distinguish between overlapping infrared signals. The mystery persisted not because astronomers lacked ideas, but because they lacked the observational precision to test them. To break through these limitations, Webb used a technique never before applied to an extragalactic target in space: infrared interferometry. This was achieved using the aperture masking interferometer mode on Webb's NIRISS instrument. Instead of collecting light as a single mirror, Webb effectively transformed itself into an array of smaller telescopes by using a special mask with 7 tiny hexagonal openings. Each opening acted as a separate collector of light, creating interference patterns when the light waves overlapped. By analyzing these patterns, astronomers could reconstruct images with dramatically increased resolution, effectively doubling Webb's resolving power over a small region of the sky. In practical terms, this meant that Webb could see details as if it were a 13-meter space telescope rather than 6.5 meters. Using this innovative technique, the team reconstructed the central region of Circinus with a level of sharpness never achieved before, marking the first extragalactic observation made with an infrared interferometer in space. When the new data were finally analyzed, the results overturned decades of conventional thinking. Instead of infrared emission being dominated by outflows, Webb revealed that approximately 87% of the infrared light from hot dust in Circinus comes from regions extremely close to the black hole, consistent with material in the torus and accretion structures feeding the black hole itself. Less than 1% of the emission could be attributed to hot dusty outflows, with the remaining fraction coming from more distant regions that previously could not be distinguished. This discovery fundamentally changed how scientists understand energy flow in the cores of active galaxies. It showed that, at least for Circinus, the black hole is not primarily defined by what it throws out, but by what it consumes. Beyond solving a single mystery, Webb's success demonstrated a powerful new technique that can now be applied to other galaxies. With billions of black holes scattered across the universe, astronomers now have a tested method to investigate how matter falls into them, how energy is released, and whether Circinus represents a unique case or part of a broader cosmic pattern. After combing through vast extragalactic surveys captured by the James Webb Space Telescope, a team of astronomers identified a small group of objects that immediately refused to fit into any known category. These sources appeared extremely tiny and compact, almost point-like, which normally would suggest quasars powered by active supermassive black holes. Yet when scientists examined them more closely, the usual quasar signatures were missing. The objects were too distant to be stars within our own galaxy, but also too faint to be quasars, which typically outshine their entire host galaxies. The contradiction was striking. Principal investigator Hao Jing Yan described the moment as encountering something that simply should not exist, an astronomical equivalent of the platypus, an animal whose features seem mutually exclusive yet undeniably real. Webb was revealing objects that looked simple in images but complex and unsettling once their deeper properties were examined. To isolate these anomalies, the research team narrowed down a massive sample of roughly 2,000 sources observed across several Webb surveys. From that pool, only 9 objects met the criteria that made them so puzzling. These 9 sources existed between 12 and 12.6 billion years ago, placing them very close to the beginning of the universe, which is about 13.8 billion years old. Spectral data, which provides far more information than images alone, deepened the mystery. The spectra did not align with known classes of objects. While they resembled green pea galaxies discovered in 2009, these new objects were far more compact. Webb's resolving power at such immense distances should have revealed extended structure if it existed, yet these galaxies remained astonishingly small and concentrated, reinforcing the sense that astronomers were seeing something fundamentally different from anything previously catalogued. The real shock came from the detailed spectral features. In typical quasars, emission lines appear broad and hill-shaped, a signature of gas moving at extreme speeds around a supermassive black hole. In these newly discovered objects, however, the emission lines were narrow and sharply defined, indicating much slower gas motion. This ruled out standard quasar behavior. While there are narrow-line galaxies that host active black holes, those systems do not appear point-like at great distances, making this combination of features unprecedented. Graduate researcher Bangjung Sun analyzed whether the data could instead indicate star-forming galaxies. The low-resolution spectra did not rule that possibility out, but it raised another question. If these are star-forming galaxies, why are they so incredibly compact, even under Webb's powerful resolution? Once again, the data refused to settle into a comfortable explanation. Rather than forcing these objects into existing categories, the research team proposed a more profound possibility. Webb may be revealing an earlier stage of galaxy formation than astronomers have ever observed. It is widely accepted that large galaxies like the Milky Way formed through the merging of many smaller galaxies over time. But what comes before those small galaxies? These point-like, platypus-like objects may represent primordial building blocks, formed quietly and compactly before chaotic mergers reshaped them into larger systems. Their appearance suggests a phase of galaxy formation that has never been directly observed until now. To confirm this idea, scientists will need a much larger sample and higher resolution spectra. For now, these 9 objects stand as a powerful reminder that Webb is not just refining existing models, but uncovering entirely new chapters in the story of how galaxies first came into existence. When the James Webb Space Telescope observed the system known as APEP, astronomers immediately realized they were seeing something no telescope had ever captured before. Earlier observations from ground-based telescopes had revealed a single shell of dust surrounding the system, and scientists suspected that more shells might exist, but they could never confirm it. Webb changed everything in one instant. Its mid-infrared image revealed not one, but 4 enormous serpentine spirals of dust, each expanding outward in the same precise pattern, like cosmic rings frozen in motion. The outermost shell is so faint that it is almost transparent at the edges of Webb's image, explaining why it had remained hidden for so long. For the first time, astronomers could see the full structure of a system that had been shaping its surroundings for centuries, transforming a long-standing hypothesis into undeniable visual evidence. By combining Webb's observations with years of data from the European Southern Observatory's Very Large Telescope, researchers were able to reconstruct the motion of the stars at the heart of APEP. The system contains 2 aging Wolf-Rayet stars that orbit each other on an extraordinarily long path, completing a full orbit only once every 190 years. During each orbit, the stars spend about 25 years passing close to one another, and it is during these prolonged encounters that dust is produced. Each close passage creates a new shell, which then expands outward, forming the spiral pattern seen by Webb. This orbital period is unlike almost any other dusty Wolf-Rayet system known. While most such systems have orbits lasting only a few years, APEP's slow, deliberate rhythm has allowed multiple shells to form and persist, stacking one beyond the other like a historical record written in dust. The creation of these shells is anything but gentle. The two Wolf-Rayet stars are racing through space, expelling stellar winds at speeds between 1,200 and 2,000 miles per second. When the winds from the two stars collide during their close encounters, they mix violently and condense into thick clouds of carbon-rich dust. Unlike dust in many other systems, APEP's dust is unusually dense and composed largely of amorphous carbon. This composition allows the dust grains to retain heat even as they travel far from the stars, making them detectable in the mid-infrared. Despite being considered warm by cosmic standards, the dust emits extremely faint light, which is why only Webb's mid-infrared instrument was capable of capturing such detailed structures. What Webb revealed was not random debris, but dust expelled in repetitive, predictable waves, each shell marking a specific chapter in the system's long history. Webb also confirmed something that had only been suspected before. APEP is not a binary system, but a trio. Alongside the two Wolf-Rayet stars is a massive supergiant star, gravitationally bound to the system. This third star plays a dramatic role, slicing through the expanding dust shells and carving out cavities that appear in the same location within each spiral. The effect is visible as funnel-like holes cut cleanly through the dust, a signature that allowed researchers to update their geometric models and confirm the star's influence. Looking ahead, the future of APEP is even more extreme. The two Wolf-Rayet stars, once more massive than the supergiant, have already shed much of their mass and are destined to explode as supernovae. Either may also produce a gamma-ray burst before collapsing into a black hole. Wolf-Rayet stars are exceptionally rare, and among the few hundred binaries known, APEP is the only system in our galaxy that contains two Wolf-Rayet stars of these types. With Webb's observations, astronomers have not only uncovered the full structure of this chaotic system, but also gained a glimpse into a violent future written across centuries of spiraling dust. When all of these discoveries are placed side by side, a pattern becomes impossible to ignore. The James Webb Space Telescope did not reveal isolated curiosities scattered across space. It revealed a universe that is far more active, far more structured, and far more deliberate than we once believed. Young stars are not quietly forming planets in calm disks. They are violently forging crystals and throwing them across entire systems, seeding future worlds long before planets even exist. Dying stars are not fading away into nothingness. They are carefully sculpting their final breath into layered structures that recycle matter and quietly prepare the ingredients for the next generation of stars and planets. At the hearts of galaxies, black holes are not merely blasting material outward as we once assumed. Webb has shown us that much of what we see is matter falling inward, feeding these cosmic engines in ways that overturn decades of accepted models. At the edge of cosmic time itself, Webb has uncovered objects that refuse classification, galaxies so small, compact, and contradictory that they may represent the very first building blocks of structure in the universe, caught in a phase we have never observed before. And in systems like APEP, massive stars move through space on century-long orbits, carving perfect spirals of dust through violence, precision, and repetition, leaving behind a visible record of chaos that somehow follows exact rules. This is why James Webb stopped the world. Not because it produced prettier images, but because it exposed hidden processes that were always there, shaping everything from planets to galaxies, yet remained invisible until now. Each discovery corrected an assumption. Each image rewrote a paragraph in our understanding of how the universe works. And together, they delivered a message scientists can no longer ignore. The universe is not simpler than we thought. It is more intelligent in its complexity. What Webb has shown us is not the end of the story. It is the moment we realized how much of the story we were missing. And if this is what the universe reveals when we finally learn how to look properly, then the most unsettling thought is not what we have discovered, but how much more is still waiting to be seen.